Have you ever wondered what would happen if you fell into a black hole? The common instinct is to picture a giant cosmic vacuum cleaner actively hunting down planets and swallowing everything in sight. But that image belongs in science fiction. A black hole doesn't reach out and pull things in from across the galaxy. It exerts a tremendous gravitational force, but only over a very limited range. Imagine replacing our sun with a black hole of the exact same mass. The Earth's orbit wouldn't change. Our planet continues traveling in its exact same circle. We wouldn't be sucked in, but without solar radiation, Earth becomes a frozen, lightless rock. At a safe distance, black holes obey the standard rules of gravity. To find the danger, we have to look much closer. These objects aren't rare anomalies. Millions of black holes are scattered right here across our own galaxy. The most massive of these sits at the very center of the Milky Way. It is a supermassive black hole named Sagittarius A star. It's millions of times heavier than our sun, yet invisible. Gravity is so intense that light cannot escape, leaving a dark void. We prove it exists by watching the environment, glowing gas swirling violently, reacting to an invisible mass. Since these objects remain invisible and harmless from afar, understanding how they function requires a conceptual journey directly to the edge of the abyss. Every black hole begins its life as a massive star. For millions of years, these spheres of hot gas produce enough internal energy to hold their shape against the weight of their own gravity. Eventually, that fuel runs out. The star loses the internal pressure holding it up, and suddenly collapses inward under its own immense weight. The resulting density is extreme. It is like taking a giant mountain and crushing it until it fits into a space smaller than a single city block. This is the core physical rule of the abyss. Squeezing a massive amount of matter into a tiny space causes the localized gravitational pull to multiply exponentially. This concentration of mass warps space itself, creating a gravity well so steep that nothing can generate the speed needed to climb out. Surrounding this well is an invisible border known as the event horizon. Think of it like a swimmer in a river approaching a massive waterfall. Far upstream, you can paddle backward to safety, but there is a specific edge where the downward current becomes too strong to fight. The event horizon is that point of no return. Once an object crosses it, even light, the fastest thing in the universe, cannot reach the speed required to escape. If you were to fall inside, the physics would be lethal. Because the gravity increases so quickly over short distances, it would pull on your feet much harder than your head. This difference in force would stretch your body into a long, thin string. Scientists call this effect spaghettification, and it would happen long before you reach the center. Crossing the event horizon guarantees destruction, but this border also serves as a cosmic quarantine, keeping these extreme physics contained. Looking at the inescapable power of the interior, we have to ask, are black holes permanent? It turns out they are mortal. Over immense spans of time, black holes slowly leak energy back into space. This process is called Hawking radiation. Molecule by molecule, the abyss slowly evaporates. This decay is incredibly slow. Even the largest black holes will take drastically longer than the current age of the universe to vanish. They are patient, but they are not eternal. Our journey shows that the primal image of a space monster is scientifically unfounded. Black holes are simply the laws of standard gravity pushed to their absolute, logical extremes. By studying the edges of these invisible objects, we are actively probing the limits of space and time. These dark abysses function as extreme laboratories. The insights gathered at their edges may eventually provide the evidence that changes our understanding of reality.